So when is the last class, by the way, anybody? I just want to plan rest of my lectures. 29th, I mean, calendar is not working. Okay, so when is the last lecture? Is it 29?
Sir, the last teaching day is 29, but you have to check.
Okay, so how many classes we have? We have today 3, 4, 5 classes. You want me to teach till the last class, 28? Okay, I'm not sure. Normally the response is no. 28th, okay, somebody was still. 28th is the last teaching day, matlab 28th tak we can have class. All right, so 5 more classes I have to cover. Let's see. Okay. Still we have the last topic, which is counters. Okay, there are many number of counters here. We will try to complete, no issues. Okay, so what is the thing we were doing in the last class was, have we started recording? Yes. Okay. So we were looking at universal shift register. We saw bidirectional shift register. What is an universal shift register was? A shift register that will have clear control to clear the registers, that will have a clock input to synchronize, a shift right operation, shift left operation, parallelly loading also, parallelly loading the registers, and it must have, when you are parallelly loading, then you must have a parallel output also, PI, PO, parallel input, parallel output, and then n parallel output lines, and then you need to have a control input. All right. So these are the things that must satisfy. We have already seen till shift left and shift right, but still I'll quickly cover. Right. So what is that? This has got a clear input. It has got a clear input. Whenever your clear is there, it will clear all the flip-flops. It will clear all the flip-flops. Okay, so first point is done. Second point, it has got a clock, right, to synchronize all the operations. It has got a clock to synchronize all the operations. So a clock here, a clock to all the flip-flops to synchronize all the operations. Okay, done. Next, shift left and shift right. We have seen this in the last class itself, but still I'll cover it up. So this requires some kind of thinking. You can implement this universal shift register using, in addition to the flip-flops or D flip-flops, you can also use multiplexers. Why we are using a multiplexer is because now we are having 3 different controls. So one control is shift right operation, then shift left operation, and parallelly loading operation. So if you have 3, you can use a 4x1 multiplexer where each one will have a certain input. So shift right, we can have it as 0, 1, 1, 0, and 1, 1. When it is 0, 0, don't do anything, right? Normal operation of a SISO input. So now let us see. When your select signals are 0 and 0, which means that all zeros will be active. All zeros will be active. What does this mean is, since this is a multiplexer here, whatever you have across this 0, you will have your output. Whatever you are having it here, you will have your output. Okay. Now let us see what is that we are having across 0. You see here that all zeros will be shorted from A3. A3, not from A3, from their outputs itself, which means that there is no change in your operation. So A1 means it will be still continuing to A1. It will continue to hold A1, A0, A2 and A3, right? So this is what is the no change operation using your multiplexer. Now let us look at the 0, 1 value. When your select signals are 0 and 1, now let us see what is that. Okay, I will erase this particular part also. So when it is 0, 1, when it is 0, 1, which is the line that will be highlighted, this particular lines will be highlighted. And whatever you have across your one input line will be available across your output. Whatever you have across one, that will be available across your outputs. Now, what is that you have across one? This is 0, 1 means it must shift right. So what is the leftmost digit? So shift right means, so this will be the serial actual input. Whatever this input is there, this will be available across A3. And whatever you have it across A3 has to be shifted to where? To 1. Okay. Whatever you have it across A2, it has to be shifted to 1. Whatever you have it across A1 will be shifted to A0 and the one input of this multiplexer and A0 output will be there. Okay. So this is what will be done when it is shift right operation. When it is shift left operation, let me again erase. Okay. When it is shift right, it is 0 and 1. When it is 0 and 1, that is, 1, 0. When it is 1, 0, shift left operation, which means that these inputs will be active. Whatever it is available across your second input, that will be available across your output of your multiplexer, which will be fed to your D flip-flop. So what is available? Shift left means what? From the rightmost bit, it has to keep shifting towards the left. So what is the rightmost bit? Where are you having this input? This is your serial input for your shift left operation. So this input now will be available across this output D flip-flop, and now this is available here. And this input must be fed back to here, right? So this input must be fed back to here, and you will see here that this comes from this A0. Similarly, A1's input must go to, you just follow this highlighted line, it will go to 2. Similarly, A2 output, it will go to this highlighted one, it will go to 2, and this output will be available always, right? That is what is your shift left operation is. Now parallelly loading. Because if you look at the first instance, you will not understand. Hence, I am doing. For parallelly loading, you must have S0 and S1 equal to 1 and 1. So whatever you have it across 3 will be available across 1. Whatever you have across 3, it will be available across 1. Okay. Now, where do you get the inputs from? This is a parallelly loading. You have to load your inputs parallelly. So your 3 will be loaded I0, I1, I2, I3 here, and which will be directly fed to A3, A2, A1, and A0, right? So this is what is called as a universal shift register. Is any doubt in understanding this circuit? Okay, all right. So regarding this only, yeah, this is what I was trying to say, that this is the function of a register for the different inputs of your multiplexers status. So when it is 0, 0, there will be no change. Your present value and your next state values will be the same. So when it is 0, 1, you will have your left operation. I mean, whatever I explained here, it has been written, so no need to worry about it. Okay. Now let us move on to counters. Many applications of out of the many applications of flip-flops, your counter is one of the most important applications. So we have already seen one application of flip-flops, which is registers, shift registers. Next, we will see what is the application, which is a counter operation. I mean, most of the places your counter is most important circuit. Then they are also used in random access memories. As a memory, you use these flip-flops. So first, let us focus towards counters. There are mainly, what is a counter is a circuit that will keep counting based on the input pulse is known as a counter. Your counter circuit will cycle through different number of states. We just saw in the tutorial class that your counter circuit will cycle through the different states. And there are two types of counters. One is called as a synchronous counter and other is called as an asynchronous counter. We saw in the tutorial class that synchronous clock, they are controlled using a synchronous counters are controlled using a clock, which means that it is a parallel clock. If you have two flip-flops, in fact, three flip-flops, all these flip-flops will be controlled by a single clock. Whereas asynchronous counters will not be controlled by a clock, but they will be controlled by the previous state inputs. I'll just, instead of this diagram, again, let me draw a rough diagram here. If you have a flip-flop here, in case of an asynchronous flip-flop, the other name of asynchronous flip-flop is called as a ripple counter. Okay, so if I'm using say one T flip-flop, then this flip-flop will get active based on the output from the previous flip-flop, which means that I will have a clock here. There will be only one clock, one external clock, and the clock of the third flip-flop will get active based on the output of your second flip-flop, right? So which means that each flip-flop will get active based on the rippling effect of the previous flip-flops. That is why this is called as a ripple flip-flop. Okay, or ripple counters. Now let us focus towards first the synchronous flip-flop. Before that, what is a ripple counter? Let us see. I've already explained. So in ripple counters or asynchronous counters, all flip-flops are not countered simultaneously. They allow some flip-flop outputs to be used as a source of clock for the other flip-flop. That's what I was telling, right? That is, these clock inputs will be fed from the output of the other flip-flops. That has been written here. Some flip-flop outputs are used as a source of clock for the other flip-flops. So this is what I was meaning. So now there are some examples of such ripple counters are, there are counters called as a ring counter. There are counters called as twisted counter. We will use multiple number of counters. We will see different types of counters, something called as Johnson counter. We will see ring counter. So we will see multiple number of counters in this class. Not in this class, maybe in this part. First, let us look at synchronous counters. Synchronous counters are also, normally they are called as, there are multiple different types. One such kind of a synchronous counters or parallel counters is called as a binary counter. We have seen this in the tutorials. Binary counter means it will follow a binary sequence. As an example here, see here, this is a binary counter. You are starting from 000, then your counting sequence is 1001, then it is 010, 011, 100, 101, 110, 111, and then again back to 0. So if you want to count, if you want to have an n-bit counter, say I want to have a 4-bit counter, then the number of flip-flops that I might require will be 4 flip-flops, and the number of counting sequence that I can have will be from 0 to 2 power n minus 1. So 2 power 4 minus 1. Okay, so 16 minus 1 is 0 to 15. So this will be my counting sequence. And as an example, if you have a 3-bit binary counter, if n value is equal to 3, I will need 3 flip-flops, and my counting sequence will be from 0 to 2 power 4 is 2 power 3 is 8, 8 minus 1 is 7. So my counting sequence will be from 0 to 7. So this is how your binary counting sequence will take place. Now, what is the design procedure? Okay. Now, in case of flip-flops, unlike shift registers, in case of shift register, you will see that there was always an external input, either X or Y. In addition to that, there was always an external output, something like Z, or sometimes there was no output also. The difference between the shift registers and counters is that you will not have any of these external inputs or external outputs. Okay, which means that these counters will have no input and it will have no output, but it will keep on moving from one state to the other state. Okay, so that is what has been mentioned here, that your flip-flops, we have not marked any input or output values in the state diagram, which means that the state transition is a clocked sequential transition which will take place on the clock edges. Flip-flops will remain in the present state if there is no clock is obtained. Okay, so what does this mean is this movement of state from one state to the other will take place only at a clock sequence, when there is, say, for example, a rising edge of your clock. So your clock sequence will be like this. Whenever you have a rising edge of your clock, then this state transition will take place. Now, clock is not normally used explicitly as input variable in the state diagram or state table, but this is, though your clock is an input here, we don't use it as an explicit input variable as a part of a state diagram. Okay, so in case of a counter circuit, the only input for your counter circuit is your clock, and the outputs are specified based on your present state table. Okay, so your next state of a counter entirely depends on the present state and the state transition that will take place. And normally you will use T flip-flops are the preferred ones. Generally, T flip-flops are the preferred ones for the counter design. For shift registers, your D flip-flops are the preferred registers, and for counters, the preferred flip-flops are T flip-flops. T flip-flops, you all know that these are complementary flip-flops. Now let us look at how to design this binary 3-bit binary counter. We will create a state table. We will create a state table with present state, next state, and flip-flop inputs. Your present state is going to, you will require 3 flip-flops, right? So A2, A1, A0. Next state will be also be A2, A1, A0. From 0, we will move to 1. If our present state is 1, we will move to 2, 2 to 3, 3 to 4. I'll come back to this flip-flop inputs later. 3 to 4, 4 to 5, 5 to 6, 6 to 7. And after 7, we move to 0. Please remember, we are designing synchronous flip-flops. We are designing synchronous flip-flop. Only in asynchronous flip-flop, as we saw in the tutorials, you will require an external reset input. We will come back to this asynchronous later. We are designing synchronous flip-flop, so which means after the last state, which is 1, 1, 1, we make it move to the next state 0, 0, 0. Then since we are going to design using a T flip-flop, we will write the T flip-flop equation. How many T flip-flops will be there? 3 T flip-flops will be there. So TA0, TA1 and TA2, these are the 3 flip-flops. Now we have to write the characteristic excitation table here. So when it is 0, 0, okay. When it is 0, 0, no toggling, so 0. 0, 0, no toggling, so 0. 0 and your present state is 1, there will be toggling, so this 0 gets converted to 1. Okay. Similarly, wherever you have 1 here, there will be a toggling. You see here, 0 gets converted to 1. When it is 0, there will be no change. So there will be toggling here. 1, 0 gets converted to 0, 1, right? You see here, there will be toggling. Similarly here, there are 1s here, there will be toggling. 0 gets converted to 1. All these places, there will be toggling, 0, 0, 0. And here also there will be toggling. There will be a toggling here. And in all zeros, there will be no change. Okay. All right. So now we have to design it. We draw the K maps for each flip-flop, TA0, Why did I write? Yeah, TA0, TA1, and TA2 flip-flops. You write the K maps. So this is for TA1, TA2, and I did not do it for TA0. For TA0, you see that all the inputs are 1 here, which means that I will give an input TA0 as a single 1 value. Okay, so now TA2, yeah, these are the 3 flip-flops. You see here that TA0, yeah, TA0 is equal to 1. So this is your TA0 input. It's already always given 1 here. TA1 is equivalent to A0. So A0 is fed as an input to TA1. TA2 is A0, A1. So A0 is already here, and A1 I will take it from here. I will AND it, and I will give it to TA2. Right? And since this is a synchronous counter, I will definitely have a clock. If you draw the diagram without a clock, then this will no longer be a synchronous counter. I will have a clock which is fed to all the inputs of a clock. This is how you will design a counters. So this is an up counter, right? Up counter means what? We are counting in the up sequence. We are counting from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and from 7 back to 0. Can you design a down counter now? What is a down counter? It has to count downwards, descending order. 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1, 1 to 0, and 0 to 7. So what will be the only change? Only change is this sequence will change. From 0, your next state will be 7, 1, 1, 1. From 1, your next state will be 1, 1, 0. Okay, I'll erase and then I'll write about this. Okay, so from 0, I'll go to 1, 1, 1. From 1, I will go to 1, 1, 0. From 1, 1, 0, I will go to 1, 0, 1. From 1, 0, 1, I will go to 1, 0, 0. 1, 0, 0, I will go to 0, 1, 1. From 0, 1, 1, I go to 0, 1, 0. From 0, 1, 0, it is 0, 0, 1. And 0, 0, 1 to 0, 0, 0 and 0, 0, 0 to 1, 1, 1. So now, obviously, I can find it. I can write the flip-flop input equations, right? So you can create in a similar manner. Any doubt here? Okay, so I've already written here that some exercise to think. Design a down counter using the T flip-flop. I've already given you the logic also, you can do it. Similarly, let us design a non-binary sequence using JK flip-flop. What do you mean by non-binary sequence is, in this particular case, it is a binary sequence. Why? Because it's 0, 0, 0 to 1, 1 to 2, 2 to, yeah, this is a non-binary sequence. Why? Because we are moving from 0. We are moving from 0 to 1, 1 to 2, 2 to 4, 4 to 5, 5 to 6, and 6 to 0, right? There are certain states that are missing. 3 is missing, 7 is missing. 3 and 7, they are invalid states. So the total number of states we have is 6 states. Still, we will require 3 flip-flops, and the 2 states are unused. So 111 and 7011 are unused. And you have to design a using JK flip-flop. So it's simple here again. Your present state is 0. From 0, we are moving to 1. Am I right? So 0 to 1, 1 to 2. So you see here 1 to 2. From 2, you are moving to 4, 2 to 4, 1, 0, 0. And 4 to 5, 5 to 6. 4 to 5, 5 to 6, and 6 to 0, 6 to back to 0. 6 back to 0. Now you have to use JK flip-flop. So you can fill up these input columns. So 0, 0, it is 0x, 0, 0 again 0x, 0, 1, it is 1x. You fill up this particular thing from the characteristic table. 0, 0, 0x, 0, 1, it is 1x, 1, 0, it is x1, right? It is x1. Likewise, you can fill up this. Now what will happen to the unused state here? Unused state, either you can put it as don't care, or you can put it as, right now we will see by putting it as don't care, okay? So what is 111 and 011 corresponds to? This corresponds to 3 and 7. Let us look at the K-map. 3 and 7 corresponds to which cell in the K-map? These two cells, right? 3 and 7. 3 and 7. They are placed as don't cares. They are placed as don't cares. And for each JA, KA, JB, KC, you get the flip-flop input equations here. And KB and KC are equal to 1. Why KB and KC are equal to 1? You see here, either they are don't cares or they are ones. Either they are don't cares or they are ones. So you can give it as 1 here. Hence, KB is equal to 1 and KC is equal to 1. Now you can draw the flip-flop diagram. There are 3 flip-flops A, B, and C. So J and K are all obviously shorter because we require a counting operation. So we want to make it use as a T flip-flop. Hence J and K are always short. Okay. No need to short, sorry. No need to short. It depends from the equation. So JA is B. So if this is JA, it will come from B. Okay, and KA is also B, I believe. Yes, KA is also B. Hence, this has been shorted. What is JB? JB is C. So JB will get its input from C. And JC is B bar. B bar is this one. Don't create a knot here. Okay, that's a bad practice. Instead, we are already having a complemented input. So this is your JB, which is fed to JC. And KB is 1 and KC is 1. So your KB is 1, which is fed to KB as well as to KC. Okay, so this is how you draw the circuit diagram. And you can also do further practice by designing the same circuit by taking unused states as 0, 0, 0, not as a don't care. What does this mean is, instead of don't care, you put zeros. Okay. Now everything will get altered. What does this mean is, if you are having a sequence as 0, 0, sorry, if you're having a sequence, if you're entering a sequence 0, 1, 1, if you're having a sequence 0, 1, 1, it will enter to 0. If you're having a sequence 1, 1, 1, it will enter to 0. Okay, so this is what it means. Any doubt here? Any doubt? Okay. Next kind of counters. You want me to repeat? I can do it. All right, so there is no doubts. Next, we will design the ripple counter or asynchronous counters. We have already seen an example for an asynchronous counter. What is this? What is that we saw? In asynchronous counters, we will have a reset signal after completing that particular state. That is called as an asynchronous counter, and asynchronous counters will not have clock, a common clock. You will have a clock, but that particular clock will be there only for the first flip-flop. Okay, so let us go to the theory and then we will solve some problems. In ripple counters, flip-flops, the output transition serves as a source for triggering the other flip-flops. Like this, I'll show you in the diagram. See here, that this is one flip-flop here, the second flip-flop. This particular flip-flop is triggered from the output from the other flip-flop. Okay, so that's what I mean. Okay. The clock input of some or all flip-flops are triggered not by a common clock pulse, but by rather by a transition that takes place in the other flip-flop. That's the same thing. Flip-flops do not change states exactly at the same time. They do not have a common clock. Yes, and this is known as the ripple counter, as input clock ripples through the counters. You will understand this better when you look at the timing diagram. Okay, let us design now the ripple counter. There are some drawbacks. What is the drawback? Obviously, you can see it is something similar to uh, ripple adders. We saw an adder called as a ripple adder, right? Because what is a ripple adder is? Because our carry in was rippling towards all the full adders. It is the same disadvantage here also, that the delay here is a big drawback here. Okay. Now, how do we specify any ripple counter? Normally, these ripple counters are specified using a mod counter, or otherwise it is called as a modulus counter. Why? Because if you have, say, n number of flip-flops, if you have n number of flip-flops, then you can count till modulus of 2 power n counter. As an example, if you have 3 flip-flops, then a mod 2 3 counter is possible. Mod 2 3 counter is mod 8 counter. 2 power 3 counter is mod 8 counter. So the mod x, what does this mean is the mod x counter cycles through x different states. When I say mod 8 counter, it will ripple through 8 different states. If I have a mod 6 counter, it will ripple through 6 different counters. Okay, and the most important is the MSBs and LSBs you must be able to identify. The output of a last flip-flop, which means that the most significant bit, divides your input clock frequency by the mod number of counters. So which means this particular counter can also be used as a frequency divider. Now you will know that you will normally, how do you divide any particular number in C program? You will take modulus, right? You will have successive modulus, right? Where you will keep on continuously dividing it by 2 till you get this remainder, right? So based on that only, these kind of mod counters or ripple counters, they are used as frequency divider also. I'll explain more what do you mean by a frequency divider when I look at the circuit diagram, the timing diagram. Now let us take an example. What is a 2-bit ripple counter is? An example of an example ripple counter is below here. Output of one flip-flop is connected to the clock input of the next significant flip-flop. Now, what is MSB and what is LSB? First, you must identify. The point where you are giving the clock, right? So you are giving the clock to the first flip-flop, right? And this is your second flip-flop. Always, this first flip-flop will be your LSB. Why? Because every clock change, this is responding, right? If you look at the input sequence, say 0, 0, 0, 0, 0, 1, I'm just writing input sequence here just to make you understand. Okay, now look at the transitions here. What transition? This is changing from 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, and 1 to 1. And here, this is changing after 2 clock pulses. If I draw the timing for this one, it will look like this. First it is 0, then it is 1, then it is 0, it is 1, right? This will be for my LSB bits. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, likewise. Now the next significant bit, let me call it as, how do I call? I call it as Q0, Q1, and Q2. Okay, so this is Q0. Now I'm going to draw for Q1. So it is staying here till 0 till the first transition. It is staying to zeros till the first transition. Once this has changed to 1 to 0, now this will change to 1 here for 2 clock cycles. Then again it will change like this. Now you see here that for 2 clock cycles, this is changing once. That is the reason we said that these are called as frequency dividers. If you look, the Q2 clock, it will change for 4 clock cycles, but at the same time, it will change for 2 clock cycles of Q1. Again, I repeat, your Q2 will provide the transition for 4 clock pulses of Q0 and 2 clock pulses of Q1. So your Q1 divides your Q2 by 2 and Q0 divides Q2 by 4. That's what it means. Okay, this is the logic. Now coming back to the ripple counter, 2-bit ripple counter, I'll just explain how the circuit connections are. Okay, first we would like to have all our ripple counters as T flip-flop, meaning JK flip-flops are shorted. Not only that, we will give a high input here. If you're giving a high input, what does it mean? It means that your present state is 1 and you want to toggle your output. So that's what it means. I mean T flip-flops characteristics. So your J and K are shorted. Now you provide clock for the first flip-flop and your output you take from Q0 bar to the next flip-flop. Why Q0 bar? I will explain now. Okay. If you are giving from Q0, then it is a low level logic. If you are giving from Q0 bar, then it is a high level logic. Now I'll explain how. Look at the timing diagram. This is how your clock pulse is going to be, right? For every transition here, every rising edge clock, there is going to be a transition. So Q0, if this is a clock, your Q0 output will be, you'll keep on toggling, right? So if this is at 1, it will be 0. If this is 0, it will be 1, likewise. Now at the same time, what will be your Q0? It will have Q0 will be complement of Q0 bar. Ideally, I should have drawn Q0 first and then Q0 bar next, so that you feel the toggling, the complement. So when this is 1, it will be 0. When this is 0, it will be 1. Likewise, they are complement of each other. Now comes this Q1. Q1 will see a transition only when there is a transition across Q0 bar. Where are you getting a Q0 bar transition here? Please remember it has to be transition means 0 to 1 transition only. Positive rising edge transition. So positive rising edge transition is taking place here. The next positive rising edge transition is taking place here. So till the time your Q1 will be 0. Once you see a rising edge transition here, it will rise to 1 and it will stay there till the next transition. During the next transition, it will convert from 1 to 0 likewise, right? So now if you look at the counting sequence now, how do I look at the counting sequence? You have to look at the counting sequence like this. Your counting sequence is which is LSB and which is MSB. This is your LSB. This is your MSB, right? So first it is 0, 0, 0, 1, 1, 0, 1, 1, again 0, 0, right? 0, 0, 0, 1, 1, 0, 1, 1, again back to 0. So we are doing a counting sequence by just rippling our clock cycles. Okay, so this is how a 2-bit ripple counter will work. We will take one more example. Maybe we will take a 3-bit ripple counter now. Again, the logic is the same. That is, all your J and Ks are shorted. All your J and Ks are shorted and they are given a high input here. Meaning that we have created a T flip-flop and then by giving 1, we want to toggle our outputs. We are providing a clock to our first clock, which means that this will be our LSB. This will be our MSB. And this particular flip-flop is getting a clock from Q0 bar and the flip-flop 2 is getting a clock from Q1 bar. Okay. Now let us look at the rippling. For every clock, for every rising edge of the clock, your Q0 output will change the transition, right? Your Q0 will change the transition for every rising edge. Here there is a rising edge, here there is a rising edge, here there is a rising edge. Now Q0 bar is complement of Q0. So Q0 bar here is complement of Q0. So this is a complemented output. When this is 0, it will be 1. When it is 1, it will be 0. Now your Q1 you will get a Q1 output only when there is a positive transition in Q0 bar. So where are you getting the transitions? I'm getting a transition here. I'm having a transition here. I'm having a transition here. And which means my Q1 will experience a transition only during these rising edges. Only during these rising edges, I will experience a transition. Likewise, I have fed my second flip-flop with Q1 bar, which means that I will require a complement of Q1 also. So what is Q1's complement? Q1's complement is the opposite of this. If this is 0, 0, then this will be 1, 1. If it is 1, 1, it will be 0, 0, 1, 1, 0, 0. And where is Q1 bar experiencing a transition? I am experiencing a transition here, and I am experiencing a transition here. And Q2 will have its states from a transition is taking place here and another transition is taking place here. Please remember, this is your MSB bit and your LSB bit is Q0. This is your LSB. Okay. Now what are the signals that we need to look at? Are we getting a counting sequence? Yes. What is our counting sequence? Our counting sequence is Q2. Our counting sequence is Q2, Q1 and Q0. Q2 is MSB, Q0 is LSB and Q1 is the middle bit. So let us see. Q2 is 0, 0, Q1 is 0 and your Q0 is 0. Next, I'll slightly zoom out so that okay. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, sorry, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0. Again it's repeating. So the counting, we got the counting sequence. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Likewise, so we have got a counting sequence, right? So this is how a 3-bit ripple counter is. Should we stop here? Maybe I'll complete this negative edge also. Now, so far, I have not answered you why we have connected this Q0 bar. Okay. Now let us look what will happen if you count the Q0 to your clock. That is called as a negative edge triggered clock. What if you connect this Q0 to a clock is, we will see the output now. So Q0 will be complemented with each pulse, which means that your next state, your Q of t plus 1 state will be a complemented of Q of t. So every time Q0 goes from 1 to 0, then the transition will take place. Okay. So if you look at the timing diagram, you will experience this. Okay. So whenever the only difference here is this will be negative edge triggered. It will not be a positive edge triggered, which means that so this is our negative edge triggered for our actual clock. And Q0, please note that we are not interested in the bars of Q0 bar or Q1 bar or Q2 bar or Q3 bar. We will look only at the negative edge transition. Where do you have a negative edge transition? Here. So this Q0 was fed to Q1. So the negative edge transition take place here. And you will experience the transition only during the previous negative edges. Previous negative edges only you will experience the transitions. You see the transition here, these transition will take place. Similarly, for the next case, there is a negative edge here, and you will have a transition here, here, and here. Yes. And in the last Q3 will have a negative edge transition here. Still, you can look at a counting sequence. Your counting sequence will be start from your MSB. Q3 is your MSB 0001, 0001, 0010, 0010, 0011. Likewise till 1111. Okay, so the only difference connecting this Q0 bar and Q0 to the next clock signal is if you connect Q0, then it will be negative edge triggered. And if you connect it to Q1, Q0 bar, then it will be positive edge triggered. Okay, so any doubts here? Okay, so we will stop here and then we will continue with this asynchronous counters with a different mod number. Okay, so far we have been counting complete 4-bit triple counter, meaning in case of a 2-bit triple counter, I'll just show you. In case of a 2-bit, so this is a 2-bit triple counter, we counted from 0 to 3. This is a 3-bit counter, we counted from 0 to 7. This is a 4-bit triple counter, we counted from 0 to 15. Next, we will see asynchronous counters, but with a mod number less than 2 power n, which means that if you are using a 2-bit counter less than 2 power n, that is less than 4. If you are using, if your n value is 3, then less than 7. If your n value is 4, then it is less than 16, right? So we will see such a kind of a counter. We have already seen these counters in our tutorials where you will use a reset signal. Okay, so we will see those examples in the next class. Any doubts? Okay, so then we will stop here and then we will meet on Wednesday.